Okay, welcome. So this is the first module in the Enterprise Networking, Security and Automation course. So we'll be looking at the concepts of OSPF in a single area. It's one of the protocols available to us in routing. So we'll describe the characteristics of OSPF, how OSPF defines packet types within a single area, and how it operates within a single area. So to start off with, let's explain what OSPF is. It's a link state routing protocol, which means it looks at each individual link and determines a cost, whereas a RIP is a distance vector protocol, which only counts the number of hops or the number of routers that it goes through to determine the cost of a path. With OSPF being a link state, it has a much larger picture of the network, and it assigns a cost based on the bandwidth of each link and adds them up. So you get a better metric or cost to reflect the true availability of the path to the destination. Now, there's a whole lot of information that it records for each link, and these links will record their network, their subnet mask, and their cost. Now, these are used when the routing protocol shares the information about each link within the topology with its neighbors. So every device learns the entire network from these advertisements that are sent out. So what are the messages that are used? Well, OSPF exchanges hello packets, database description packets, link state request, link state updates, and link state acknowledgements. These packets are used to discover neighbors. They're also used to advertise their networks to their neighbors. So we'll go through these at the appropriate time, but in effect what they do is they send a hello to discover each other, then they'll send a descriptor of their routes or networks, links, and then their neighbors will request further details if they needed to. And that's when you get the updates and acknowledgements coming into play. So within this routing protocol, it creates a series of databases. Now the first database is an adjacency tape. Now this is a list of all its neighbors, and if you want to look at it, you can view this table with the show IP OSPF neighbor command. The next one is the link state database or topology table, and this database represents all the known networks within the topology. Now, all the routers if it's a fully converged network, should have identical link state databases. You can view this database with show IP OSPF database, and from that it will build its forwarding database, which is where the algorithm runs and determines the best path or paths to a destination. And this will be used to inject into the routing table, and we can view the routing table with show IP route. So what algorithm does it use? It uses Dijkstra's shortest path first. Now you're thinking, how difficult is that? Well, if you've got GPS, you're basically using it. All right, so basically it looks at all the alternative paths to the destination and creates a cost. All right, so you have this, all your lists of your paths or your networks, goes through the algorithm and it builds this little tree up, picture of the network, and it works out the cost to get to any point in the topology. And it takes the best path and puts it into the forwarding database. And these are then presented for the device's routing table. So to gain this overview of the topology, the network needs to converge. Now, convergence is where all the routers have the same information, and they do this by establishing their adjacencies. The link states are then exchanged via advertisements. They build their link state database of all these little bits of information, and then they run their algorithm over that link state database to get their paths or routes. Now, OSPF is designed to support a very large network by being very efficient and scalable, and does this by having a very strong hierarchical approach to its design. And we implement it based on two concepts: a single area. Now this generally, as a best practice, is known as Area Zero. Area Zero is the core or the backbone of OSPF. And as we scale up, we turn that single area into multiple areas, and we do this so that they all attach into the core Area Zero. And the boundary router, the one device that sits both in Area 0 and Area 10, for example, is known as an area border router. Now, these border routers are responsible for summarizing all the routes within Area 10 and injecting them into Area 0. So with this approach of scalability, we can build separate, discrete areas that function autonomously, in that all the routing information is shared within its area between all the devices within the area. only the area border router is responsible for sharing into the other area. So we limit the amount of administrative traffic that is used to maintain the area. So this makes it more efficient overall, and each area can converge faster and become more stable. So a change in one area may not affect other areas, because unless it changes the summary of routes, the updates do not go outside of the area. But for the rest of this chapter, we'll be concentrating on area 0. Okay, so here's the benefit of each area being connected together. So you get smaller routing tables because we don't have to have every single link or network in our routing table, because as I said, each area is summarized. The link state updates are reduced because they're only within the area. So here we have a link going down in area 51, and it sends out updates for the change of the link state to all the other devices in area 51. And what they will now do is recalculate their routes based on this updated information. So area 0 and area 1 aren't impacted by that, because router 2 will only update area 0 if the summary addresses change, which is not necessarily the case. If we've designed our network correctly, all of these can be summarized into 1 or 2 route statements, and they are injected into area 0 rather than each individual component. Makes for an overall more stable topology and less calculations. Now, OSPF version 2 was IPv4. Okay, so with the advent of IPv6, we had an update to the routing protocol so that it could exchange information for IPv6. So it has the same features as OSPF version 2, it's just enabled for IPv6. And it also changed the way the networks were incorporated into the protocol. So there are some changes, but those changes have also now been incorporated into OSPF version 2 so that they are compatible moving forward. So within the curriculum, there's a nice little video that's used to explain how these packet types work. I'll let you view that as you go through. But basically, what we're looking at is 5 packet types. Now, these link state packets are used, and basically they're the same between version 2 and version 3. First one is the hello packet, and this is used to discover and build adjacencies between devices. Type 2 is the database description, and these are used to synchronize the information between devices. So the database is basically a big summary of all the links that it knows about. If a device wants more information about one or more links within the database description update, it will then request the specific records. The link state update is the reply to that request with the detailed information of the links. And then you have type 5, the acknowledgement of the receipt of the update. So the updates can themselves be broken up into different elements. So these are link state advertisements, and so link state updates and link state advertisements are interchangeable in a lot of instances. So the types available of LSAs is router advertisements, the database synchronization, so type 2s, summaries, which is like the descriptor, autonomous system external LSAs. So the summary advertisements are used by the border routers. Autonomous systems external are used as representations of the external from the area. Okay, so you've got summaries. Autonomous system externals are outside of the areas. There's more to it than that, but I'm not going to go into it at this because this is just an introduction and we're not doing multiple areas. Multicast, stubby areas and not so stubby areas are unique special areas that are available. We'll cover those in detail when we do multiple areas. External attributes such as used for border gateway protocols. So there is great flexibility in OSPF. We can send updates and advertisements between areas, summarize them, external to the area. These will behave different to internal ones. And the people that designed the protocol realize that there are circumstances, such as when organizations merge, that you may not be able to connect directly to the core. So they came up with a way to tunnel through another area to get to the core. And that's what not so stubby areas are basically used for. And then this is the outside world, so that's where type 8 comes in. So the hello packet, I'm not going to go into every single field, just be aware of the main ones. The type is important because that defines the packet type. The router ID is used to tell its neighbors where the source of this packet is and what area it's working in. The timers for hello interval and dead are important. They must match. So area, hello, dead. If they don't match, they're not going to be sharing your information effectively. Then we have designated router and backup designated and list of neighbors. So in this list of neighbors, it will have a list of every other device it's received a hello packet from. So once device A sends out its hellos, if it receives a hello from device B and it sees itself in the list of neighbors, it has a neighbor relationship because it's got two-way communication between them. All right. Other little quick thing, network mask. So this is where the networks are residing. Router priority, that, and can be used in the election of the designated router and backup designated router. This we'll go into detail more in a little bit, but basically wherever there's multiple access networks such as Ethernet, where there can be a potential of more than 2 routers sharing OSPF information, there needs to be an election. On point-to-point links, where there is only the potential of 2 devices, there is no election. So again, little video on how it operates. I might actually spend some time in a future update and extract the video and insert it into the PowerPoint. But until then, you can just go off to the curriculum and watch the video. It basically describes the 7 states of operation, which we'll discuss. So, downstate. So this is where we're not receiving hello packets from anybody. We're issuing hello packets and trying to transition to the init state. The init state is where I've received neighbor packets and they contain the router ID of the sending router. Two-way state is where, as I said earlier, communication is bidirectional. In other words, in the hello packets, it can now see its own router ID in the neighbor packets received. So it knows an exchange of information is now possible. We will now have an election in a multi-access network to elect the designated router and backup designated router. More to that later. It will then try to transition after the election requirements to X start state. Now, this will be where the database packets are exchanged, and in point-to-point links, it doesn't have an election, but it has a pseudo election because it still needs to decide who's going to exchange that database first. So it has a little discussion, uses almost the same process to work out who's going to exchange packets. Exchange state is where the actual database packets are exchanged and the routers will request additional information. And as this is being absorbed, it transitions into loading state where your requests and updates for specific information are sent and received. They start running their algorithms to determine their paths and then transition to full state where they have a complete link state database and it's fully synchronized with the other devices within the network. So the router ID, this is a 32-bit number, basically exactly the same as an IPv4 address. All right. Now this is used to identify each router or device running OSPF, and each device needs to be uniquely identified to build this neighbor relationship. These hello packets that are used are sent to all the others using a multicast address of 224.0.0.5, and any device running OSPF version 2 knows to listen to this address and receive the updates. Now, you can manually set a device's ID. It can be dynamic, automatic, but this is not recommended. It's not best practice because there is issues with the router ID. So just be aware, and I'll discuss that when we show you the configuration. I'll remind you why that's the case. So to establish an adjacency, a interface needs to be engaged in the OSPF process. So on an interface that's enabled, it'll start to send the hello packets. And I'm not going to go through all the transitioning again, but be aware that the hello packets, as described previously, will go through, be sent out, and as it receives hello packets from other devices, it now includes those IDs in its hello packets in its neighbors list. And this is how all the devices eventually learn of all the other devices as those hello packets are forwarded throughout the entire network so that everybody gets to see everybody and understand where they reside within the topology. So as all the devices synchronize up, they will decide who has the highest router ID. Now this determines who's going to send their database descriptor. So they become the first one, they exchange it, and the receipt of that is acknowledged. Then the other devices will send requests to get detailed information that they're missing from that database descriptor, and then the original device will send updates out. This enables the entire topology to synchronize and move to full state. Now, under normal circumstances, these are incremental updates. As links change, only the change notifications are sent out, or when devices turn on for the first time. But there is a timer. So after every 30 minutes, it'll redo this process to ensure that everybody has the same picture, regardless of the incremental updates, just in case something went wrong in the updates. Why do we need a BOS, a designated router? So we do this because the number of adjacencies that are required increase exponentially as we get more devices. So it becomes a bit of a mess as to who's going to control messaging. So it's much easier if we kind of have a central point to manage the updates. Okay, so as a rule of thumb, the number of adjacencies in a multiple access network is the number of devices to the power of the number of devices minus 1 divide 2. So for example, we have 5 devices, so 5 to the power of 4 divide 2 is 10. So there's 10 adjacencies required. The lovely link state advertisements need to be flooded. Okay, so because of all the adjacencies throwing all this information around to all the other devices, we start getting more and more administrative packets consuming bandwidth that should be used for data transfer. So for this reason, we have a designated router. Now, this is in charge of receiving all the updates or LSAs, and then they will forward it on as a unified update. So basically the way it works is the designated router combines all the changes in topology and sends it out as one advertisement to all the devices. So rather than having everybody talking to everybody over each other and it being a confusing mess, we have one device going, send me all the updates or change notifications, and I'll send out a combined notification out to everybody else. So it's not good to have just a single point of failure in our network. So this is why we have a backup designated router that also is listening to all the individual change notifications, but it is silent. Its job is to maintain the records, just like the designated router, but it's listening to see whether the designated router is sending out those combined updates. If it doesn't hear from the designated router within a set amount of time, it takes over. That's the purpose of the backup designated router. All the other routers within this little adjacency field are designated as DR other. They're not a designated router and they're not the backup designated router. They're just another router. And summary time. So we had a quick look at open shortest path first. We noted that it's a linked state routing protocol which works differently to a distance vector routing protocol, and that this is a very scalable network. It can work over a very large network, and it can do this by scaling the administrative areas that are affected by its management. So by segregating itself into designated areas, you can maintain smaller, more concise advertisements and updates. So effectively, changes are confined to within an area and do not affect external areas. This makes the protocol more efficient, easier to manage, and consumes significantly less resources in the overall network than alternatives. These updates are sent whenever a change occurs, not on a timer. So they're also not the entire routing table as is used within distance vector. They are only sending the change notification. The exemption to this is when devices first boot up and they need the entire exchange so that they can synchronize with the topology. How does this work as far as synchronization? Well, we have 5 types of packets: the hello, database description, link state request, link state update, and link state acknowledgement packets. They're used to form adjacencies or neighborship relationships with other devices, and then are used to exchange link state databases with each other, and from that, specific requests for more information on any missing links or networks. Each link is a separate, unique network within the topology. And we saw that the Dijkstra shortest path first algorithm is the core of this protocol and is used to calculate the cost to any given destination within the topology. Once we have synchronization occurred, we'll have a elected device that is known as the designated router, and its job is to collect all of these individual link state advertisements from all the other devices and send out one combined LSA to the networks with the routing protocol. So we have one definitive source of updates. Now, as I just finished saying, it's a bad idea to have only one definitive source, so we have a backup designated router. Now, backup designated routers only exist when there's multiple access networks, i.e. Ethernet. They don't form when there's a point-to-point link, but the election process, where it uses a combination of the router ID and the priority field to determine the election. So basically the one with the highest IP or ID is the winner. So at the start of the ID is the priority. So if they're all running on the default values, it's the router ID that is used to determine who's the boss. And you generally do that on the highest address. Second highest will become the backup designated router. Now these packets that are sent back and forth contain the router's source ID, the area so that it's not advertising to another area, the network masks, the hello interval, dead interval, the priority for the router, and who it believes is the designated and backup designated routers, and a list of all the other devices it knows. This is how they develop a picture of the overall topology. Okay, so they all talk to each other, whereas a distance vector will only talk to its neighbor, and it will only build a view of the world based on its neighbor's routing table. So it won't necessarily know all the individual ways of getting to a destination. It will only know the topology based on the view of its neighbor. Whereas in a link state protocol, the view of the world is based on it learning every single network. So it's its own view of the world, not its neighbor's view. These updates, the hello packets, are sent to 224.0.0.5 multicast address. So every device running OSPF version 2 listens to this address and picks it up. We also discussed the fact that as we get more devices running the protocol, we have an increase in the number of adjacencies that each device needs to form. These adjacencies and relationships, if they're not managed via the process of having a designated and backup designated router, would become quite chaotic in that, you know, if we have 5 neighbors, we need to form 10 adjacencies. So that tells you that if we've got 20 routers, there's a lot more adjacencies and a lot more advertisements and updates being exchanged, causing this chaotic environment. So this is why we have the single source of updates. So by only one or two devices listening to the individual updates and then sending out a unified update to all the other devices, it makes the whole process more efficient and limits the amount of traffic being generated to maintain the router's view of the world. That concludes our introduction into OSPF. The next one will be on configuration. So I hope you join us for that one. Until then, have a nice day.